Now let's look at some thin film interference examples, and there's actually 4 possible cases. And going back to, we'll have constructive interference if the distance that one wave has to travel, whether to another, in this thin film is an integer number of periods. So if one has to travel one full period longer than another, then they'll constructively interfere and it'll be very bright, for example, for visual light. If my delta L shift that one wave has to travel when it goes through the thin film and comes back, that total distance traveled is half a wavelength, then it'll be destructively interfering. And for thin film, we must consider not only the delta L length between, because I got to go there and back, so that's, my delta L is always going to be twice the thickness of the film. I have to go through the film and then back. So then my total travel is 2L. So that's a consideration. The second consideration is there's a possibility of a phase shift only on reflected waves at both boundaries of the film. So I could reflect off the front boundary of the film, and I can reflect off the back boundary of the film. In both, I do reflect off the front boundary and the back boundary of the film, and there's a possibility I have a 180 degree or pi or half a wavelength phase shift at each one of those cases. So there's 4 possibilities. We'll look at the first one here, a soap bubble, which is a thin, so here's my thin film. And all I worry about, man, I could have air and soap and all other kinds of stuff in glass on one side of this, of lots of thicknesses. But all you're going to focus on is you're going to think about, all you're going to just think about is the thin film and what's the media immediately on the incoming side and what's the media on the back side. So we're just thinking about that. So here we have this soap bubble, and we're on the outside of it, and we're looking in, and we see, and the light's traveling through air, and then inside this bubble is another air. So now we define the medias we're interested in. The media in the thin film itself, the media on the incident ray, and the media on the backside. So, and what we really care about is 2 things. We care about which one has what's the ratio, or which one has a greater index of refraction, the film on the incoming side, and also the film on the outgoing side. So here we have in air, let's say index of refraction is just like 1.0003, and let's say in the soap the index of refraction is something like 1.2. So it's greater than that in air. So therefore and it's greater than both sides. So we know now this. Also, just to help us understand, we know whenever I have a high index of refraction, I have a low velocity. So we know this is where the velocity is the slowest in the slow film, and also because it has low velocity and frequency is constant throughout this wave, we'll assume it's a singular frequency wave. Therefore, the wavelength in the soap film is less than in air. And all we're going to care about in the solution ultimately is not the wavelength anywhere else except in the wavelength of the media, because we're going to go a certain delta L in this media, the one that just reflects off the incoming side just goes a short distance. The one that has to go through it and then through it again, so 2 film thicknesses is delta L. That one cares about the wavelength in that media. It doesn't care about the wavelength anywhere else. So that's a critical one to remember, is we always need to consider wavelength in this thin film media. Okay, so that's the first part, and that'll give us part of this delta L. And then the other question is, do I get apparently some free delta L as a result of reflections? And so we're going to look at 2 cases, two places where the only 2 places I'm going to have reflection is I'm going to have reflection when it at that first entrance boundary, and I have reflection on the back side of the film. And so reflection has a phase change if the media that's reflecting off of has a higher index of refraction than the media that's already in. So that's this case right here. So soap has a higher index of refraction. It's my low velocity thing, and so I draw this wave in here, and I drew it with some angle here relative to this, just to understand it more, so I can show the reflection. But I just draw it, and I put a pi there. So I know right away that this wave this reflected wave had a 180 degree or a delta a wavelength over 2. I mean, so you could also say, this gets this is a pi, or it's a wavelength over 2 shift. Okay, but I just typically just put pi there. And then let's look at possible phase shift here. So now the index of refraction of soap is greater than air, and for that case, I put a 0. I don't have a phase change. I don't change reflectively some wavelength. So now if I'm an observer here, there's my eye. I'm looking and I see these 2 waves coming out. I see the one that just bounced off the front, and I see the one that went through and then came back. Bounced off the back surface, reflected off the back surface, came back in there. So now I have these 2 waves, and one of them had a 180 degree phase shift, or half a wavelength. The other one had no phase shift. So right away, if I want these to construct, and I want the delta L to be either 1 wavelength or 2 wavelengths or some amount of that, I've already gone half away just from the reflection. So as a result of the reflective state change, the 2 waves are reflected already have a phase shift of pi radians. So all I need is another half a wavelength. So I got half a wavelength already. I just need another half a wavelength in order to get them to totally construct. So the delta L total only needs to be at a minimum. I mean half a soap film wavelength. And so there I'll say delta L. We know delta L is always going to be 2 film thicknesses, because I got to go there and back. So my total distance traveled by this wave has to go farther than this one is always going to be 2 film thicknesses. And in this case, at a minimum, I'm going to have my delta L. I need to go that half of a wavelength in the soap film farther. And then in more general case, I mean, where m is 0, I go half. Where m is 1, I have to go 3 halves of that. But let's solve for the minimum right here. And so if I just want to solve for the T film thickness, I'll just take this 2, put it over there, and I find out my minimum film thickness for construction is 1/4 of the wavelength of the soap film. And then if I wanted the next one, if I had a soap film that was a little bit, that was thicker, and it would actually have to be 3/4 of the soap film wavelength. If you just put if you put a 1 in there, you'll see that if I had that soap film 3/4, I'd also get the same case where I'd have constructive interference. And then we know that essentially then if it was half, then that would be totally destructive interference. It would be dark. Okay, and what's also critically important is it's critically important to know this is the wavelength of a frequency, that just matches. So red, yellow, I mean all the spectrum of colors will all have different wavelengths, or they have different frequencies which give them different wavelengths, and so there's only one color that'd be exactly right for this condition. And it's critical to remember that you need to use, because we're getting delta L's in the soap film, you must use the wavelength in this thin media. And so if you're given the wavelength in air, you must convert it to the wavelength in the soap film, and that's just we know is take the wavelength of air times the index of refraction of air over the index of refraction of soap. And since the index of refraction of soap is greater than the air, we show that we're getting the wavelength of soap shorter. So you solve for that, plug that in there for the wavelength of the soap, divide by 4, and that's the thickness of this thin film that would give you constructive interference. That's the minimum film thickness. Now we said there were 4 cases. So this was the first one, and you can think about if I have at the first boundary my index of refraction, my index of refraction coming in, or backside. In this case, the index of refraction went up, and then it went down on the backside. So that's one case. I could also have a case, where the index of refraction goes up and it goes up, or in a case where the index of refraction goes down and it goes up, or it goes down and it's down. So there's 4 possible cases. And we're going to talk about 3. We're essentially going to talk about cases that are 3 of the 4 cases. And we'll see where the answer is either 1/4 of the wavelength in the thin film or 1/2 the wavelength in the thin film. So let's look at this case right here. Second example, we're going to tackle the problem identically. So we'll go a little faster. So let's say we have oil film. Oil was on the ground, it rained, and oil is less dense than water, and so oil rose. The very thin film of oil rose to the top, and I'm standing up here in the air, and I'm looking down, and what I see is I'm in the air, and I have this very thin film of oil, and light's coming from the sky, reflecting off this oil on top of water, and this oil is my very thin film, because it's very, very thin on top of that water, because there wasn't much oil there. So that's my problem. And so what do? First thing, we constantly say, what's the media that's the thin film? Well, that's oil. So don't worry about anything else. I don't worry about if there was something under the water or something. It doesn't matter. It's just all we care about is the thin film, what is media, and what's the media on each side of it. So I have air, thin film, which is oil, and water. And then you worry about index of refraction. So index of refraction of air is low, like 1.003, and let's say this is 1.2, and then water like 1.33 for frequencies of visible light that we're concerned about. So we have now this scenario that index of refraction is getting higher and higher and higher. And then if we think about velocity, so the velocity of the electromagnetic wave is the fastest in the air, then it gets slower and then slower. And same thing for wavelength. Wavelength is long and it's getting shorter and shorter. Okay, so now we're going to think about this ray coming from the sun, and we're looking back, and all we're going to see is two rays reflecting. One reflecting off the top surface of that oil film, and one reflecting off the back surface of the thin film. So what happens at this boundary? I'm going from a case where I have a low index refraction to a high index refraction, and therefore the reflected wave sees a pi phase shift, or you can think about it, it's a pi is half a wavelength. Okay, so that's one does, and now what happens here when I have this reflection? Again, I'm going from a low index refraction to a high index refraction, so I'm going to have a pi phase shift, or a half a wavelength. You can think about it. Okay, so now we know both of the. So now I'm looking, and both of these waves had half a wavelength phase shift. So right away, if this film thickness was infinitely small, was essentially 0, I'd be constructive already. Okay, so that's one case. If the film thickness is 0, it's constructive. But this film actually has some thickness, and so let's look at the next thickness where I get it. So what do I need to have for constructive interference? I need my delta L to be a full wavelength again. So delta L is always 2 film thicknesses, because I gotta go half the L. I go there and back, so my total length traveled is 2 film thicknesses, and I need some integer numbers of wavelengths to get construction. Okay, and the shortest one other than 0 is when M is 1. So now sticking in here, 2 times the oil film thickness equals two times the thickness of the oil film equals the wavelength of the wave we're considering in the oil. So so m is 1, right? So now I can know that my oil film thickness is going to be half my wavelength. So in addition to 0, I can do half a wavelength going that way and half a wavelength coming back, and now we're constructively interfering. So there's my solution for the oil film thickness. Okay, and then if I wanted to where it would be totally dark at this wavelength, so obviously that'd be 1/4 of this oil film wavelength. And then the next oil film thickness would be constructively interfering would be at 1 full wavelength of this oil film. And again, remember that we must, in this formula, since we need to have the wavelengths happening in this thin film, that's the wavelength we care about. So the wavelength, if I'm given the wavelength in air, we know that this wavelength in the oil film is smaller, and it's by that ratio. Okay, and if I had the opposite case where I went from, I'm not showing it here, but if the incoming light was this way and I had whatever medium I'm in the water, and then a film, and then air, and I do this is my thin film. Again, this time I would have 0 reflection, 0 phase shift, and a 0 phase shift, and I get the same answer as this. So that's one of my 4 cases. Now the last 4 cases is to consider I have 2 glass surfaces that are relatively pretty flat, but there's some little air gap between them for whatever reason. Okay, and initial waves coming this way, and once again, I'll take the answers out of here. I'm looking at these 2 different reflected waves and trying to say, do I get some additional motion change in length here because of phase shift? Well, so air, this is my low index of refraction, these are higher. This is my long wavelength one. So I'm coming into this, and so I'm going from glass to air, going from a high index of refraction to low index of refraction, and so I don't get any phase shift on that reflected one. But then when I go from now I've gone to this air, on the backside I'm reflecting off glass. So in this case I do get my pi phase shift, or you can say it's half a wavelength. Okay, and then I come out and there's my observer, and he looks and he sees one that went longer, actually, in addition to going longer, went half a wavelength already. So all that's left is the other half of the wavelength. Well, it's gone. The delta L is 2 thicknesses. So 2 thicknesses, I need that half a wavelength at a minimum. And so look again, if I look for the shortest one where I constructive interfere, I can take this divided by 2, and I get 1/4 of the wavelength in air. And then so therefore that's constructive. The destructive one would be half a wavelength in air, etc. So this is these are 4 examples of thin film interference and what you must consider.